There's a name for the certain types of equations that we've been looking at that implicate derivatives, equations that often involve integration. These are called differential equations. These are simply equations that have derivatives in them. Now, they're sometimes called ODEs for ordinary differential equations. Sometimes this is abbreviated to DiffEQs. Whatever terminology you use, we're going to be working with differential equations. Motivated by some of the examples we've just looked at, we're going to consider differential equations on some function x that depends on time, t. These equations are going to be of the form dx dt equals some function f that can depend on x and or t. A little bit of terminology is in order. Such an equation is called a first-order differential equation because it depends on the first derivative of x. We're going to spend some time thinking about these differential equations, what they mean. For starters, what this equation means is that if you know your present, you can determine your future. If you know your current state x and what time it is t, then you know dx dt. You know how your state is changing. And with work, you should be able to figure out x as a function of t, how your state changes with time. In general, this is kind of difficult. If we look at a particularly simple class of differential equations, something where the right-hand side doesn't depend on x, but only depends on t, then we have dx dt equals f of t. How do we solve that for x as a function of t? Oh, you know how to do that. We know the derivative, so we anti-differentiate. X of t is the integral of f of t dt. Just don't forget the constant. For an explicit example of this integrating a differential equation to get a solution, consider the following example. Let's say you want to solve dx dt equals 4t minus 3 sine t. How do you solve that for x? Well, x of t is the integral of its derivative. It is the integral of dx dt with respect to time t. That is, we're integrating 4t minus 3 sine t dt. How do we compute that integral? No problem. We anti-differentiate one piece at a time via linearity. The antiderivative of 4t is 2t squared. The antiderivative of negative 3 sine t is positive 3 cosine t. And we have to add a plus c, don't forget that. And we're done. That's it. That is what is called the general solution. And as we've seen before, it comes in a one-parameter family. That depends on this constant c. That's the general solution. You might want a specific solution, where, let's say, you have specified a particular value of x. Let's say x at time 0 is 0. This is what is called an initial value problem. You're given the initial value of x. Well, in this case, what do you know? You know that when t equals 0, our general solution, 2 times 0 squared plus 3 times cosine of 0 plus c, must vanish, must equal 0. You can solve that for c. You will get c equals negative 3. And that will give you your specific solution, your specific x of t. Now, you don't need to use an initial value. Any value would do. You can specify, let's say, x at t equals pi. Let's say that's equal to 4. Then what do you know? You know that 2 times pi squared plus 3 times cosine of pi plus c equals 4. Once again, solve for c. In this case, you'll get 7 minus 2 pi squared, and you're done. That is the solution that satisfies this condition that x of pi equals 4. Now, that was a pretty simple example. Most ODEs, most DiffEQs are more challenging to solve. But finding solutions to ODEs, that's a really important use of calculus, of integration. Now, just to be clear, what do I mean when I say solving an ODE? Typically, one is given the differential equation and you want to find the solution. For example, let's say that you are asked to solve the differential equation dx dt equals x minus t. Let's give an initial condition. Let's say x of 0 equals 0. What do you do? What's the solution? The solution is some function x that depends on t that satisfies this equation and the initial condition. Now, I'll tell you that in this case, the solution x of t is equal to negative e to the t plus 1. How did I do that? Where'd that come from? How did I get that? I'm not going to tell you yet, but I am going to show you how to confirm that this is, in fact, a solution. And it's easy. You just check it. If I assume that x is negative e to the t plus 1, let's compute its derivative. dx dt is what? The derivative of minus e to the t is, of course, minus e to the t. The derivative of t is 1. The derivative of 1 is 0. This simplifies to x minus t. Right? If I take that expression for x, remove a t, I get negative e to the t plus 1. That's dx dt. That means this works. This putative solution is, in fact, the solution. Checking, of course, that x of 0 equals 0. Now, in general, finding solutions to differential equations can be hard, can be not so obvious. We're going to, for the moment, stick to differential equations that are maybe not so bad to solve.